A softball diamond is a square with 60-foot sides. A runner runs from second base to third base at a rate of 10 feet per second. How fast is the distance from the runner to home plate changing when the runner is 20 feet from second base? Well, here's home base. Here's first, second, and third bases. D labels the distance between where the runner's at, running from second to third base, his distance from the home plate. So the question is, can I find DDT? Just don't say that fast 5 times in a row. Well, here too, everybody, I think I was told something about how x's change with respect to time t. I was told something about dx dt, but it's too difficult for me to build an equation relating dx dt to dd dt. So I claim defeat, and I merely build a relationship between b and x, treat them as functions of time t, differentiate implicitly with respect to time t. Now, obviously, a clean relationship between these two quantities in my pretty picture is the Pythagorean theorem. And I certainly think the Pythagorean theorem tells me that the hypotenuse squared is equal to this. Now, can you imagine as time goes by, this triangle changing? This leg doesn't change, but the length of the hypotenuse and the length of the other leg do change. So treating both of those as functions of time t, differentiating implicitly with respect to time t, does that give me this? Now that I've differentiated, I get to take that mathematical camera out of my back pocket, take a snapshot in time, and put in the equation all the information I get from that pretty picture. So at this one point in time, I've lost my numbers. At this one point in time, the runner is 20 feet from second base. But that's 20. That's 60. So x must be the difference, which is 40. Now the runner is running at a rate of 10 feet per second. So replacing dx dt with 10 feet per second is certainly a mistake. Because if he's running from this base to this base at a rate of 20 feet per second, sorry, I meant to say 10 feet per second, don't you agree that x is going to decrease in size? And so I think the rate of change of x is actually, numerically speaking, that. Excuse me. I will not put anything in for dt. That's what I'm trying to find. But notice, just like with my last example, I was not given the value d. So here too, I need to take a nifty little break. I'll pull out a piece of scratch paper. And at this one point in time, here's a right triangle I'm looking at. And so to find d, I will yet again use the quadratic formula. So at this one point in time, d holds a value of 20 root 13. That suggests the following. So notice as time goes by, d is decreasing. That's why its rate of change is negative. Can you also see why we refer to these as related rates questions? Because I'm relating the rates at which these two quantities, d and x, are changed with respect to time t in this equation, but I generated it by first looking at a relationship between x and d and differentiating implicitly with respect to time t. Oh, those examples are too simplistic. Maybe we can up with the next one.